Hello everyone. These are the apparatus for black box experiment. This is what we call it as black box, and there are three components inside this box. So each component is connected across each one of these two terminals, and the components are inside. And our job is to find out which component is that. It may be a resistor, it may be an inductor, or it may be a capacitor. And by doing an experiment, we should figure out which component is connected across which of these terminals. And as well, we have to find out how much is the component value of it. Means if it is a resistor, how much ohms or kilo ohms it is. If it is an inductor, how much Henry it is. Or if it is a capacitor, how much Faraday it is, you have to find out. So to find out, the technique we use is by using the alternating current. Means you know that when you supply an AC through these components, each one of them responds differently. The resistor will not change any of its voltage or current across it as you change the frequency. Mean, a capacitor, if you increase the frequency, it starts allowing the current through it, and for inductor, if you increase the frequency, it starts blocking the current through it. It's because in inductor a back EMF is going to develop, and in capacitor the displacement current will increase and it starts allowing the current. So let's find it out. The circuit diagram for this experiment is as follows, this one. So here this X represents the component which is unknown component, one of this, and the terminals of these two are written here, and this is audio oscillator, which is the one which generates AC signals for us. So this is audio oscillator for that, and the AC current from the audio oscillator should be fed to the component through an ammeter. So ammeter is to measure how much current is going through it. So this is ammeter, a digital ammeter given for the measurement, and an voltmeter should be connected across the component so that you can find out how much is the potential difference across the component. So for voltmeter we are going to use digital multimeter. This is a digital multimeter, so with which you can measure the AC voltage. So right, one by one let me introduce you to the apparatus for that. So this I already introduced, the ammeter, and the black box I introduced, and this is the multimeter. So the multimeter can measure DC voltage, AC voltage, DC current, and as well as the resistance of any of the component. So here what we are interested is to measure the voltage of the AC which you are feeding across the terminal. So hence you are supposed to use this multimeter in this mode because you are measuring AC voltage. Don't go for DC voltage, or don't even go for this DCA. DCA doesn't mean that DC is something with AC nothing. So it is for A stands for ampere and it is for current measurement. Don't use this. Don't use this or this one. Use ACV. Why ACV? Because you are going to feed AC signals to the circuit. From where the AC signals are coming? So they are going to come from this waveform signal generator. You can see this is waveform signal generator with which you can produce AC signals of desired frequency. The frequency can range from 1 Hz to 1 megahertz, and you can even change the voltage of the AC voltage which it is going to produce, and don't hesitate that it may give you shock because it is AC. Why it won't give shock? Because the voltage is very less. The maximum voltage it produces will be just 20 volts, and the AC which we get in our households are about 220 volts. They are going to give a shock, but not these things, so that we can touch here, not a problem. So fine, the settings wise, you should have some preliminary setting for the signal generator. The settings are as follows. I will switch it on first. So usually the button will be in the back side. You can turn on. The display is showing. The display actually shows the frequency of the AC which it is producing at its output, and the frequencies can be selected through ranges. You can see it is written 10, 100, 1K, 10K and 100K, which means if you press, say for example, this 1K, then you can have all the frequencies running from 1 Hz to 1 kilohertz. If I change the button to 10K, I can get it in kilohertz. if I get it in 100k, still more frequency I can obtain, but for this experiment 1k is enough. So we are going to change the frequency in terms of 100 Hz, 200 Hz and so on. For that this 1k is more than sufficient. So just press this button 1k, that's it. And here this is toggle switch to see the frequency and voltage of it. See, it is now showing frequency, and you can see here one more, it is showing it is Hertz, which means whatever the display it is showing, it is in Hertz. So fine, now if I press this, it is going to show something else. So now you can see here, if you press the button, so then it is going to show the output voltage which it is producing. If I remove this one, then it is going to show the frequency of it. So just to check. So now this is the thing to set the voltage. So better setting is to set it to full maximum, 21 volts it is giving. And these two are the buttons. If you want to have lesser voltages, then you can press and achieve. Say for example, see now 21 became 2. If I click further, it became 0.02. So don't do it. So let these two buttons be outside. So, and this should be full maximum. So fine, then other things are there. This is DC offset, it should be minimum. And here other three buttons are there. This signal generator can produce a sinusoidal wave, triangular wave and a square wave. For our experiment you need sinusoidal wave. So let this be pressed and other two be unpressed. And this is symmetry, you can even tweak the symmetry of the sine waves which you are having. So let that be off. So let it be minimum and let this button be unpressed. So don't press this, let it be outside. And this should be minimum, this should be minimum, and this level should be maximum. Fine. So now let it read frequency. Now you see, for doing our experiment, I want it to set to some frequency, say 100 Hz. Then I can use this coarse knob to set the frequency. See, if I increase the coarse knob, it is increasing, but it is going to increase at faster rate. A small twist in this knob is going to increase frequency at larger rate. So what you do is you use coarse knob as well as fine knob to set the frequency. Say now I want to set it to 100 Hz. What I will do is I will come close to 100 Hz or little less to that. See here. Then I am going to use this fine knob and slowly increase. Now you can set the frequency to exactly 100 Hz. Let this be the first frequency for which I am going to do the experiment. Now what I should do, I should feed this AC signals which are coming from this signal generator to this black box, to the first component. We are going to do one by one. First let me do for the first component. And as far as circuit, you can see that the circuit says you have to feed these AC signals coming from this to the black box through an ammeter. So to get the output, you need to have something called as this coaxial cable. So for handling AC signals, usually the coaxial cables are used, and this is the BNC connector. So it will have two wires in it. Actually, it's a coaxial cable. One core will be there, and one more outside, one more wire will be there. So now you can see inside one tip is there. This is one terminal. The outside case is another terminal. Where you have to plug in? You have to plug in here. There are two, don't get confused. Many students go wrong in this one. This TTL is for some other purpose. TTL means transistor logic. Don't use this. Here, this is the one you should use. It is written func, means it is function generator. So, or the whatever the functions you choose here, that will be produced from this one. So now what you should do, you should plug in. So how to plug in? Just insert it. You can see it. And just inserting is not enough. It is wrong connection. Just to do it, it is not good. Insert it, then twist it so that it is fixed very sturdily. So then after that, so at the end of this wire, so there will be the branching. I said it will have two wires inside. So now it comes out of it. Since it is AC, don't worry of plus or minus. Just think it as ground and a phase wire. And now what we have to do is we have to connect it to black box, right? So for that you should go through patch cards. So because all these things are this kind of connectors, so this is a banana clip. So what I will do is I will first have this connector wire, and I will connect it like this, right, so that I can take the another end for my experiment. And this is another one I am going to take. As I said, the circuit connection is very simple. So what we should do is, one wire which is coming from this AC source has to go directly to the component, the first component of this black box. So where it is here, just plug in. So another one should go through the ammeter. So this is digital ammeter for AC measurement. Switch it on. So now you see, you can connect it for the thing, and from the other side you take and then let it end at here. Fine. Now AC is fed into the component of the black box through this ammeter. So fine, now I have to measure what is the voltage across this component, right? So then for that I am going to use this digital multimeter set at AC volt measurement. That too, there are two things, 750 and 200, two ranges. The meaning of it is, if I have it at 200, it is going to measure AC voltages till 200 volts. If I have it here, it is going to measure AC voltages till 750 volts. But you see that at 200 you are going to have 1 decimal point extra accuracy, right? See, there is a point something. So for 750 you don't find it. And now you just saw that the voltage is within 20 volts, around 20 volts. So you don't need to use 750. Just use this minimum one, the 200 one, so that you will get more accurately. Fine. So now how to connect this one? So connection should be taken through these things. There are three inputs for this. So first one is common, it is compulsory connection, you should always take from here. And this last one, you can see that it is written 10 amps DC. This is for special purpose. It is for current measurement, high current measurement, high DC current measurement. So don't use it. So then another one you can see here, V ohms milliamps, it is written, use it here, right? So if you use on the other side, you are not going to get proper readings, right? So fine. Now so from these two, where I should connect? So it should go parallel to it. You can just see the circuit diagram once again. See, the voltmeter is connected parallel to the component. So where is the component? Component is across these two terminals, which is inside. The component will be inside the black box. So now how to connect this voltmeter? So just take it. So these patch cards are going to have one more one more connection slot. So through that you can, from sidewise you can make a connection. So if you don't get it, you just see it, I will show you. So it is like this. So there will be one more sidewise hole. So through that you insert. So then you can have one more cross connection for that, right? So now you are having the measurement of the AC voltage. So now can you see, for 100 Hertz, whatever I am feeding to this first component, I am reading 6.4 volts of AC and 6.6 or 6.7 for the current. If it is oscillating 6.6 and 6.7, just take the one for which it is going to stay longer. See, 6.6 is staying longer and 6.4 is the voltage reading. So now you have to tabulate those readings, right? The tabular column is like this, the observations. This is for the first two terminals. It is written here in the black box as A1 and A2, the same convention I am following. For terminals A1 and A2, for 100 Hertz, you should note down voltage and current. How much is voltage? So here you can see it is 6.4. You just take it as 6.4. And how much is current? Current is 6.6. And one more note here, the current which you are measuring is in milliamps. It is written here 200 mA, that is the maximum capacity of this ammeter reading. But whatever the numbers it shows, it will be in milliamps. So don't miss it. When you are calculating, that 10 to the power of minus 3 coming out of milliamps should be taken care. So like this you tabulate the reading 6.4 and 6.6 voltage and current in milliamps. Similarly now you should do for 200 Hertz, 300 Hertz and 400 Hertz. This is for terminals A1 and A2. So similarly you should do for terminals B1 and B2 and C1 and C2. For them also you should you receive. No. You should be in control that you can set it exactly to the desired value. Set it. What you do is first try with coarse knob and then use the fine knob and slowly adjust. You see I can exactly set it to 200 Hz. Fine. For 200 Hz, what is the reading? You can see 6.6 as the current value. You can see. And voltage value is 6.3. The first tabular column I am showing you. You can see that as the frequency is increasing, the current and voltage are fairly constant. You can see it is maintaining constant current and constant voltage. So which component it is? So it is a resistor. So resistor doesn't change their current and voltage values as you change the frequency. So then another terminal, the second terminal B1, B2, you can see that as frequency is increasing, the current is decreasing and voltage is remaining almost same. So when it is going to reduce the current, so which component it is? So it is an inductor, because of the back EMF it is going to reduce the flow of current through it. So that is the one. So the last one, you can see as you are increasing the frequency, the current is increasing and voltage is fairly constant. So then this is a capacitor. For capacitor, as frequency increases, it starts allowing the current. So then once you found all these things, you should write the conclusions here. So which are the corresponding components on this side? So I will write the first one is a resistor, and second one is inductor, and third one is capacitor. So just make a note here. So in this place, a resistor and an inductor and a capacitor. So now the last part left over is we figured out which component it is: inductor, capacitor and resistor. So next thing we need to do is we have to find out what is the component value, means how much is the inductance value, how much is the capacitor value, and how much is the resistor value we should find out. So for doing that you can use the formulas for the impedance, so which are if you know the frequency, current and voltage, you can figure out the component value. So that will be for the calculation part. So I will show now the sample calculations for 1 or 2, and from that we will fill the tabular column. We noted down the readings, and we also found what are the components connected across the terminals A1, A2 and B1, B2 and C1, C2. You can see that we identified across A1, A2 there is a resistor, and we found the voltage and current values for it, and from it we can calculate what is the resistance of it. The resistance is given by R equals to V by I, and you can pick one by one the first reading, and of course the resistance value is not depending on frequency, and just voltage and the current values we should take one by one. For the first reading, the voltage value is 6.4, and substituting it you can get R equals to 6.4 volts. Whenever you are substituting, it is better you substitute along with the units so that you don't go wrong. Divided by 6.6 milliamps, and milliamps means it is 10 to the power of minus 3 amps, because the current we measured from the meter is in milliamps. So it is 6.6 into 10 to the power of minus 3 amps. So simplify it by using calculator, and 6.4 divided by 6.6 6.6 equals to 0.969, or if I round off it is 0.97. So it is 0.97 into 10 to the power of 3 ohms, or we can call it as 0.97 kilo ohms. So this is the resistance value found from the first reading, and similarly find out the resistance for other readings also. For the second reading, voltage is 6.3 and current is 6.6 milliamps. So it is 6.3 divided by 6.6 into 10 to the power of minus 3 amps. 6.3 divided by 6.6, 0.954 or 0.955, 0.955 kilo ohms. So the whatever the component value you calculate here should be written back into the table to the corresponding reading. So you can now add the unit for this component value. The component value now I am going to represent in terms of kilo ohms. For the first one it is 0.97, for next one it is 0.955. Similarly you fill this table for all the readings, and in the end you average all these values and write down how much is the average value of the component and report it in the result. So this we did it for the first table, and for the second one I just showed you the sample for 2, and actually in your data sheet all these steps should be shown. It is better to have all those things. So similarly I will show for terminals B1 and B2. So B1 and B2 we found it is an inductor. For inductor the inductance value is given by L equals to V by 2 pi F into I, where F is the frequency of it, and you are going to get the value in Henry. Henry is the unit for the inductance, and I will substitute for the first reading. You can see the first reading which I am having is for 100 Hertz. I am having voltage as 4.2 volts and current as 50.1 milliamps. So let me substitute. So L equals to 4.2 volts divided by 2 into 3.14 into 100 Hertz is the frequency into current. Current is 50.1 milliamps. Milliamps is 10 to the power of minus 3 amps. So if I substitute and simplify it in calculator, I will get 4.2 divided by 2 into pi into 100 into 50.1 to minus 3, 10 to the power of minus 3. So I get it as 0.133, 0.133 Henry. So if you substitute everything in SI unit by having it in amps, volts, hertz and all, the unit will turn out to be in Henry. So similarly calculate, and once you calculate for that component reading, you write it back 0.133. Here the component value, it is in Henry, it's an inductor. And similarly do it for the remaining readings for all of them and tabulate it and find the average inductance value. And similarly one example I will show for the terminal C1 and C3. Sorry, C1 and C2. So terminal C1 and C2 we identified it as a capacitor, and for capacitor the capacitance value is given by C equals to 1 by 2 pi F into V, and the capacitance unit will be in farads. So let me substitute the first reading. For the first reading, C equals to 1 by 2 into 3.14 into what is the frequency? Frequency is 100 Hertz into the voltage value. Voltage value is 6.7, and sorry, it is not 1, it is I divided by 2 pi F into V. Sometimes some students confuse this, whatever the formula printed in the manual, it's actually I. Some people confuse it with 1 and just simply take it as 1. It will be wrong, don't do that. it is I, which is current. So here the current value is, for the first reading it is 1.9 milliamps 10 to the power of minus 3 and 6.7 volts here. And if I simplify it using calculator, it is 1.9 exponential minus 3 divided by 2 into pi into 100 into 6.7. So I get it as 45 into 10 to the power of minus 6 farad. It is nothing but 45 microfarad. So tabulate it back. So here for the component value it is microfarads. I'm going to represent. It is 45. If I want to add some more decimals, 45.1. Can have 45.1. So like that, calculate for the remaining values and fill it, and then take average of the capacitance value in microfarad and report it in the result. So that's it. So this ends the calculations for the black box. From this we identified what are the components present at each terminal of the black box, and also we computed what is the component value for the respective components. Thank you.